A very good morning to one and all present here. My topic is flow networks and Fulkerson method. So the depth fluid terminology is residual network, augmenting path, Fulkerson algorithm, and one example. So where the Fulkerson algorithm, for understanding what is Fulkerson algorithm, we need to understand what is max flow. We will understand what is max flow and what is flow network first. What is flow network? We will understand what flow network is nothing but directed graph, right? Directed graph G is equal to V comma E, where each edge has a capacity. Capacity is basically the weight. Capacity is greater than or equal to 0. So for going from here to here, we will have some weight, right? So that is the thing. Flow network is nothing but it is a directed graph where each edge has some capacity. Capacity is this only, right? See here you can see C of S comma A is 3 and C of S comma C is 3. So this is capacity. Capacity is the same thing what we call as weights. And here in this network, in flow network we have two special nodes, that is the source and the sink. We call this as sink. Sink is represented with the letter T and source is represented with the S. So these are the two important vertices which we will be using, that is in the flow network. And we will understand what is flow. Flow is nothing but it is a valued function. It is represented with f, small f. This small flow f in G. G is like the graph what we have here. We have here also the same thing. This it is a real valued function. V cross V means from this vertex to this vertex. That so you have some value from here to here, right? That is, this is the capacity. Flow is like you will get from here to here. You will have a flow. Flow and capacity is represented with flow by capacity. So this is one is flow, 3 is the capacity. So here for the having the function flow, you need to have these three criteria. One is the flow of U to V. Something from U to V is like from one vertex to another vertex. There it has to have a capacity less than this. The flow should have the flow value should be less than the capacity. And f of U comma V is minus of V comma U. That means from see here f of S comma A is 1 means flow, that is flow, not capacity. If flow from here to here is 1, then from here to here it will be minus 1. And for every vertex that V doesn't belong to S and T, that is the source and sink, then we have f of U comma V is equal to summation of U comma V is equal to here f should be there, summation of f of V comma delta. So that means this is nothing but it is telling like what is incoming should be outgoing. So that is known as flow conservation rule. And this is called as Q symmetric. And this is flow capacity. Flow capacity rule. This is capacity rule. This is Q symmetric. This is flow conservation rule. All three following will consider the flow. So here you can see the example of that. The same for this what we have taken for flow network. For this we have taken the flow. Here from here it is going 1 by 3, 1 by 3, 1 by 1. We have considered here 0. Here we have considered 1. We are maintaining the flow in such a way that incoming should be equal to outgoing. Max flow problem. For understanding Fulkerson method, we have to understand what is max flow problem. Max flow is from going from source to sink. We need to maximize the value. So maximize the flow. So will be the max flow problem is we have to maximize the flow from S to T. That is the source to sink. We have to increase the value. The total amount of flow from S to T is 2. How we will understand it? Like from here, it should go till here. So here you see. If the flow value is summation of U that belongs to be f of S to U. S to U is from here till here. and here till there. So we'll get the value as 2. How we'll see this in detail? See here, this is the value of the, we will have summation of u belongs to v, that is f of s comma u minus u comma s.
Sorry. Okay, sorry.
So this value is 0 from u to s. This value is 2. So we are considering only this value. So this value is 0. And here we are taking flow from the source is equal to coming out sink. Here, see, here we are having from source we are 1 by 3 is coming and 1 by 3 is going. So these 3, 1 by 3, 1 by 3 is going. And here at the sink you are receiving 1 by 3 and 1 by 3. So what is going from the source should be received at the sink. So we have to understand one more terminology, that is what is residual network. Residual network is residual, you can call it as residual graph also. It is represented with G suffix F. There is same graph. You have the graph, you are making it as a residual by increasing the flow. See, consider a valid flow from F1. Valid flow is something from S to A to C, then C to T. One flow is this. Otherwise, you have S to B, B to C. What is going from source to sink is that is called one flow. From your source, you are going to the sink. That is one flow. We will consider that as from here S to A to C, then C to T. This is one diagram. This is another diagram. We will understand what is this. See, consider a valid flow F in the network G. The residual network has the same vertices as the original network, and 1 or 2 edges in the original. So in the residual network, what we are doing is we are increasing the flow. So what we are doing, we will consider one flow initially, flow F. We will consider a flow. That will know for that we have to increase the flow. So what we do, we consider a path such that we have same vertices as the original, and we are keeping 1 or 2 same vertices which we are taken in the original. So from C, one vertex is this. So again we will consider one. This is the same vertex what we have considered in the initial flow. So this will be considered as the same vertex. So 1 or 2 will be common in the what we have considered before and what is considered in the residual network. So this is the condition for forming the residual network from this to this. So there are two conditions. If f of u comma v is less than c of u comma v. C is the capacity, f is the flow. U comma v is from one vertex you are going to the another vertex. So if this flow is less than capacity, then you will form a forward edge. See, here you are forming a forward edge. Will form a forward edge such that C of f is, we are considering C's capacity. C of suffix f, that is residual capacity. So here what we will do, see, from here to here going, the capacity is 5. This is the capacity. Value of this is 5. So from B to C, the capacity is 5. So what we will do, capacity minus flow. 5 minus 1, you will get 4. You will consider if this, see, if this flow is less than capacity, then you will do 5 minus 1, 4 and consider a forward edge. So that is what this full statement is saying. If you have this one, flow is this is less than this, so you will consider a forward edge by making this 5 minus 1, 4. And if the flow value is greater than 0, then what you will do? If it is not 0, see, here we have 0, here we don't have 0. So we will have a backward edge with the same what we have the capacity. If what we have the flow, that one will make it as capacity. So there are two conditions. Understood, everyone? See, the two conditions is, see, if you are having from a flow is greater than flow is, you have flow is less than the capacity. 5 is greater than 1, right? So you will have a forward edge that will be 5 minus 1, 4. And the flow is greater than 1, greater than 0, it is 1. So you'll have a backward edge with the flow value. Understood? So this is what we consider. See here 5 minus 1, 4, and here backward edge 1. Here you see, you have 2 minus 1 is the forward edge we are constructing, and the backward edge is the same value. So this is what the term is. If you want, you can note down this. So one more important terminology is the augmenting path. Augmenting path is very important because Fulkerson algorithm is also called as augmenting path algorithm also. Why? Because if there is an augmenting path, then alternate path which is increasing the flow, then only we can consider the path, right? From the residual network, if there is a augmenting path existing, then only we can consider a flow which is great, which has max flow. Basically, we are increasing the flow to maximum value. So an augmenting path is simply a path from S to T in the residual network whose purpose is to increase the flow. We are basically increasing the flow. We'll get a residual network. We have to every time check in the Fulkerson algorithm. Like if you are having an augmenting path only, we can proceed. Otherwise, we'll exit. So that is like a while loop. In the residual network, if there is existing augmenting path, then only we can go to the next. Otherwise, we have to stop. That is whatever we have the value, that is the max value. So here one of the example we have. So this G of f is the residual network. We learned residual network or residual graph. So whatever we constructed from the same last, that by using the residual, we know the two conditions for the residual network. One is that we considered we had a value 5. So based on the residual network, we considered like one more path, because here we had 5. We considered that 4 and 1. Here 1 we had. Here we got a backward edge because here we had 1 only. So we will get a we will not get a forward edge, so we will get a backward edge over here. In this we are considering here this is the graph we learned for the residual network. So this is from here we are checking if we have an augmenting path. That is, we are having in such a way, we have a path in such a way that we can increase the flow. So here we will check. See, first we saw that we considered this one. Then by using this residual network, we found this from S to B. This is the what we did in the last one to get the residual network. So now we'll check in such a way that we have flow value. Here we have the flow value is 2, because here you see, here you have 1 S2 from source to sink it has to come. We are considering this part. So see, first we are having this path. So we using this we'll construct this one. By using this we'll get flow. We are increasing the flow value. Here from this here the same rule. Here you have flow value is greater. Flow value is greater than the capacity. So we'll have the forward edge 2 and the backward edge with 1, 2 and 1. And here again same 2 and 1. And here we have same, right, 1 and 1, so we'll get a backward, same for this what we got, backward, we'll get a backward edge. So Fulkerson algorithm, this is the main algorithm we have to learn. Fulkerson algorithm is used to find the maximum flow in a network. It is we used to find the maximum flow. So the main objective is to find the maximum flow. It was developed in the year 1956, as the name said, by the two persons. The one is Ford, the other is Fulkerson. It was developed in the year 1956. So this Algorithm is also called as augmenting path because it is based on the augmenting path. If the augmenting path is existing, then only we can increase the flow value. Otherwise, we have to say the same thing. So this is the method what we are using. Ford Fulkerson method. This is the graph G. This is the input. This is the source and the sink. So we initially the flow will be zero, initialized to zero. Then we will see if there is an augmenting path in the residual network. Then residual network is in the starting, whatever the graph we are getting, that only we are considering as the residual. Then we are seeing the augmenting path and increasing the flow. Flow is that from source to sink we are getting a path which has a greater flow value. We are augmenting the flow along the P is the path, augmenting path, and we are returning the F value, the flow value. Flow value is whatever we are maximizing it. So here is one of the example. See here you have from here to V1 we have 16, from here to here you have 12, here to here you have 20. So initializing, what was the algorithm say? 0. So from S to V1, V1 to V2, V1 to this. So first we will consider this part from source to sink. This one we will consider S to V1. See, this is the path we are considering S to V1, V1 to V2, V2 to T. Source to sink we are considering one path. And here we will find which is the minimum value among, this is the 16, then 12, then 10. Among 16, 12 and 20, 12 is the minimum, right? So we will take the minimum value for finding that, and we will divide 12 for the flow. We are taking the flow value, right? Flow value is basically a function value that we are considering which is the minimum value, and we are taking that as the flow value. So 12 by 16, 12 by 12, 12 by 20. So only for the path we are considering, that only we are giving the flow values. Here you see from here till here we got this. So here F value is 12, but because the minimum value what we got is 12. Then from there we are considering the residual network. So we know the two conditions. You will only will see this one because the path is only this much. See from here we will consider the residual graph or residual network. So 12 is less than 16. So we'll have a forward edge with 12. We have 16 minus 12. The value what we know. 16 minus 12 will get 4 as the forward edge. Backward edge will be 12 because the C of u comma v is equal to f of u comma v. So backward edge is 12, and here we have 12 minus 12, 0. So here we have to have 0. Here we will get 20 minus 12, that forward will get 8, and backward will get again 12. So 20 minus 12 is 8. Then again here backward edge will be 12. So that from this residual network, again we will consider the here flow value will be 12. Right? We will consider a path such that we are maximizing the flow. Now we will consider another path and we will. So this we have considered the residual network we got right. So from this again we are considering another path. Now we are considering this path from S to V3, V3 to V4, V4 to V3. Now here we will see what is the minimum value what we will get. Here here the minimum value is 16. So F value we will consider 16. Then after that we will consider this what is the residual network.
Minimum value is for 16.
16. That is the thing. See, minimum value is 4. So here you are adding this to the flow. So here you can see this is the path we are considering. S to V3, V3 to V4, V4 to V3. Now we will consider minimum for F value. We will consider minimum 13, 14 and 4. Then 4 will be the minimum value. Then from 4, then you consider our residual network. Then the same path again will be increasing. So here you see, here you will increase. Here again you will get one more arithmetic pathway because 4 by 13, 4 by 14, because that 4 value was the flow value what you got. 4 by 13, the forward edge will be 4 minus 13. What is 4 minus 13? 9. And the backward edge will get 4 again. Here we will get 14 minus 4, 10. Forward edge, backward edge, again 4. Same here also. We will do same. And here we will get this. Here backward edge is this. Okay. 4 is this thing. Forward is 0. So from this again we will consider one more, and the maximum value we will get for the max flow is 23. So basically we are increasing what is the max flow we are finding out. So this is the algorithm what we have in detail. Fulkerson G, S, T. G is the graph, S is the source, T is the sink. For each edge U, V belongs to G, E. G is the graph, E is the edge. Okay. So U, V into F is equal to 0. While there exists a path from P from S to T. So you have to have a path, right, for increasing the flow. From source to sink, you have to have a path. So if there is a path existing, then only we can consider the residual network. Then the residual network, how we are finding the residual, the minimum of whatever we are having the values. You got right. We had the 14, this thing, and one more thing. So among here we have only 3, so we are considering only 3. So from source to sink, how many values we are having? Based on that, we will take the minimum value. We'll make that as CF of P. Then for each edge, same thing what we did. Again here, if we are seeing if this thing is for making the residual network, the forward edge and the backward edge. So this thing, then you are increasing the flow. Whatever you are getting for the previous value, we are adding the new value. So the first we had, I think we had 12, then we got 4. So we are adding that value to the 4. So we are adding, otherwise we are subtracting it. And the time, this is the algorithm. The time complexity is E into F. F is the flow, E is the edges.
It is not fixed.